Okay. If people have problems with the Zoom, usually the OBS is in much better resolution, and I actually keep an eye on the chat right now, and I'll put in the chat of the Zoom the link to the Twitch address. Guys on Zoom, can you hear me? Yeah, the computer will get relaxed in a second once it's moved some stuff, but also at the same time, still the resolution is better, and I keep an eye on the chat room. You can stay on Zoom at the same time. It's better, but go to Twitch to Alon ALG. Okay, let's talk about homework 3 and then continue with various hashing thingies. More advanced. Hashing, and quickly also covered how do we handle collisions that you probably have seen in other courses, but a few other things that you didn't see. And probably the material for the midterm we'll cover today and Wednesday, and probably that would be the cut of what the midterm will cover. There's definitely things about hashing. Okay, almost. So there was various things that you can do with flow. There's many more things you can do with flow, obviously. Among the questions that I thought it was resolving is, I have a set of intervals. I have a set of intervals, and I want to, and I'm looking at the big interval from 0 to 1. Hope that the quorum will relax in a second. And I'm looking at the interval between 0 to 1. If you got bad quality in Twitch OBS as well, then it means the computer seems to be very, very occupied, and I know that Chrome is running various things. So maybe I can close. Yeah, we'll give it another minute, and if it's not relaxing. So we have a set of intervals, and we are looking at the big, let's call it a segment, or the universe, or whatever we want, the universe between 0 to 1. And out of all these intervals, I1, I2, I3, I4, we want to generate covers. C1, C2, C3, as many as we can, as many as possible. Create covers. What is CI? CI is a set of intervals out there. You cannot slash an interval in the middle. You cannot double use an interval. And we want as many covers as possible, but a cover must mean that all the points from 0 to 1 are in the intervals in a cover. So a cover is a subset of the intervals. For example, a cover here might be I10 is a cover because it covers everything from 0 to 1. I20 union with I21, I20 and I21 is a cover, because this union this covers all of it. I'm giving the intervals different heights just for visualization. They're all on the x-axis. They all live on the x-axis. The y value is meaningless. It's just so that we can see them differently. So the hint, of course, let's use flow to find a maximum set of intervals. Please don't take pictures. We want to cover it all, and we are asking how can we solve it as a flow. The question asks to find 17, because otherwise the wording becomes too obscure. But if you can find 17 different covers, then you can find as many as possible. The 17 doesn't have any meaning by itself. So how can we solve it using a flow? We want to make a flow problem out of it, namely, what will be a good set of covers? Let's go to the other side. What would be a good, how do I know if I found a good set of, if these three intervals forms a good cover? It would mean that from the point 0, I can send the flow into I1, that can send a flow, the same amount of flow, into I2, that can send this flow into I3, that can send the flow back to 1. I see a lot of nodding heads, so hopefully people did realize it before. So what do I mean that, how does the interval have such a high Q to decide to which other interval to send it? So basically we're saying every interval has a lot of chances. It can send its flow to a lot of other intervals, provided that what? I1 is capable, or we allow I1 to send its flow to any interval any one of these intervals are a good target to the flow of I1, provided that this one of the other interval I2, I3, I4 is starting before I1 ends. Make sense? So when I'm generating my graph, I1 will be a node, and I2 will be another node, and my graph is directed, of course. It's going to be a flow problem. So from I1 to I2, I'm sending an edge. From I1 to I4, there is an edge. Why? Because I can send a flow between. Similarly, from the point 0, that is becoming the source of my network flow, from S to which interval can I send the flow? Every interval contains 0. Which intervals can send the flow to 1? Every interval that is ending at or after the point 1. That's it. So that will be your graph, and now you are finding maximum flow. And if your flow is integers, then think about it. What it will be a maximum flow, integer maximum flow in this network? Well, if you track the flow as it moves from one interval to another, to the other way to 1, then it obviously must be a cover, because there is no missing point of the interval between 0 and 1. I'm either inside an interval or move to another interval, but they must be overlapping somehow. So I can move from left to right and cover everything. Admittedly, a bit tricky question. Okay, why do I know that I find the maximum number of flow, the maximum number of covers, 17 or more? Well, because my max flow algorithm tries to find as many as possible paths in this graph that starts at S and ends at E. And if I'm using Ford-Falker sum, then, or ILP, then I know that my solution will be an integer flow, meaning that for every edge either I send a flow or I don't send a flow, but I don't send half a flow. Okay. So that was the question for the interval. If you are here, there is a little question that was question B that is slightly orthogonal to it. It's not used in the global algorithm. Like a very reasonable algorithm, but it's not optimal, but a very reasonable algorithm for this question would be, let's try to find the minimum set of intervals that cover 0 to 1. Find the minimum set of intervals that cover 0 to 1, remove them, and repeat. And if you gave an algorithm for find the minimum set of intervals, then you will get a big bonus points if you proved its optimality. That is, that what you're getting is the minimum set, as few intervals as possible. In my case, I had one interval I10 that covers the whole thing, then I can do it with I1. And again, that's not how the solution works, but it's an interesting by itself. And what will be the algorithm? Anybody sees? Again, orthogonal question, find as few intervals as possible that covers 0 to 1.
Among all the intervals, starting 0, take the largest one.
Among all the intervals that start at 0, takes the one that takes you as much to the right as possible.
And then update the lower bound from 0 to the feedback.
And then from A, try to find the interval that takes you all the way as far as possible to the B. Out of all the intervals that gets to this point, take it all the way from this point, all the way to A here. And you can easily show that this will be the optimum. That is, takes the optimum and shows that the first segment, what does the first segment of the optimum solution will be? Well, you can replace whatever is the first segment in the optimal solution will be, you can replace it by the first segment you suggested and get no worse than what the longest segment will do. And then greedily continue with the longest segment of each iteration. So yeah, it's a good point. Thanks. But as I said, the meaning here was to solve it with flow. Okay, so this computer doesn't like a Chrome. I think that I remember the other questions. Other questions from homework 3. To find a set of paths that uses every edge only once, that is not too hard, just use a max flow, and as long as it's integer flow, then you know that you are not, that if a flow that starts from S, if your flow reaches along some set of edges T, then because the capacity of each one of these edges is 1, then and its integer flow, then it must be a path that carries a flow of 1 along all these edges, or along all these edges, and similarly another flow of 1 along this path. Of course, the set of edges along the first path and the second path are disjoint. Why are they disjoint? Because the capacity of each edge is 1, and we force the flow to be 0 or 1. So if an edge can dedicate all its flow either to this path or to this path, but not to both. It cannot be half and half, or 1 and 1, because its capacity is 1. So that was how we are making this flow to be edge disjoint. What will you do if I want this flow to be vertex disjoint? I didn't ask it in the homework. I'll ask it in the midterm maybe. I want the flow to be meter disjoint. To be vertex disjoint. That is, if your vertex are on one path, then they cannot be on another path. So why don't you take 2 minutes and check it between yourself, because it's a good dynamic. So I want a set of paths such that the set of vertices on each path are, the set of vertices are disjoint. When I'm looking for a solution so far, it's quite possible that this will be a solution to the problem so far. You have a vertex V here in the middle, and V is used on the first path, V is used on the second path, it's parallel edge disjoint, but not vertex disjoint, because V is on both of them. So take really 2 minutes and please tell me how to find vertex disjoint path. People on Zoom, I had to close Chrome, and I don't want to open Safari in real time. So if you have questions, please use the Zoom chat. No pressure, but unless you know the solution, then the idea is that you talk to your neighbors, whatever your neighbors are. I should have arranged you to see differently, but you guys. Also, you should first. Well, it's a good point why it doesn't work, but you take by mistake the wrong vertex, and you can. So I'm not putting my neck that it will necessarily not work. I think, but by picking a path and removing my work. The unit is solve it with materials that we discussed.
But you don't constrain, if you don't put any constraint,
I think that I have a solution of an example of why your solution doesn't work, but I'm not 100% sure that I'm making it big. My first path somehow destroy for the future path. So no, think flow. Okay, let's take another 30 seconds.
And to give you a feeling about the difficulties, I would think that that's an easy question, given the other questions that we played with, not given other things that we discussed, not if you're approaching it as from scratch. Okay.
Okay, so we will do what you suggest in the question 1b, that you will transform the graph into graph G into G prime, where each vertex we add each vertex B we transform it into U and U prime and U2 prime, yes. And when we set the capacity to 1. Yeah, exactly.
So the solution is, of course, limit the flow over every vertex to B1. The original method for flow was limiting the flow through every edge to 1, but didn't care how much flow goes through a vertex. If I make sure that through a vertex there is a flow at most 1, then I'm happy, because now if it's integer flow, I cannot have a flow of 1, or a flow of 2 through a vertex. So how can I do it? Well, I suggested 2 ways to look at it. If you're looking at it through you can phrase the constraints about each vertex directly if you are using LP/IRP, or the more standard way
is to use very common trick about graphs. We will use similar tricks.
When we talk about shortest path, and we want to say shortest path in a graph is counted as path in vertices, not necessarily path in edges. That we are paying for going through a vertex as well. We are taking one vertex U that has a vertex, it has an edge from W to U, has an edge from U to Z. And we are replacing U by a pair of vertices. That's where we are moving in another question from n vertices into 2n minus 2 vertices. That is, we are replacing U by U prime and U double prime. All the edges that were originally connected to U are now connected into U prime. All the edges that are coming from U to another vertex Z, remember, directed graph, are now coming from U double prime. And I can place capacity on the vertex itself, which is, if it's 1, it will mean
it can be on one path only.
And that's now I find max flow. And
what will be the running time if I want polynomial running time? What will be the running time?
You
can do it faster, but at least specify something.
And power by 3.
And 3. Yeah. Number of vertices to the power of 3, or in other words,
all the of how many vertices do you have in your network times how many edges do you have in your network. N times M. That's the time of basically we are running a for Falkerson that we'll talk about more. At each iteration, you increase the flow by 1. And it takes a linear time to increase the flow by 1. You need to kind of explore all the vertices in the graph, and the graph has M vertices. Why M is more dominant? Because we assume that the graph is connected. In a connected graph, you have more vertices, more edges than vertices. But almost it's n minus 1 if your graph is just 2. So you have at least as many edges as vertices, possibly more. So that would be the running time of a Edmonds car. Okay, let's. We had a question. About the making all the words, storing a set of words. We had a question of storing a set of words that suggested an idea that I want to reinforce. Originally, I used my terminology. I want to take the input, shifting a key or maybe transforming a key. Transforming a key into a canonical form. It's my terminology to call it canonical form because it's common to express it in a similar way in other problems. So of course in problem TF14 it was trivial. You have to store the word hello, and you now want to insert this hello, and you want to find this hello, and it should be, of course, the same word. And we just need to decide what is the canonical form of this key. How do I express it so that no matter how you give me the input, I can transform it to a different input? Again, I'll take your input, the word hello that in the spelling that you gave me, and I'll transform it into another input. It will be really trivial. In this case, I'll transform it from either this case and from this case into the canonical form. And what is the canonical form? I decide. I will specify what is the canonical form that I want for this input, and there is no correct or incorrect. It's up to you. Just what you want to make sure is that these two hellos will look the same way. Okay, so for example, write it with small letters, we'll do the trick for you. Right.
Just transform it both ways into small letters.
And then for correlation 14, you have to use the dot product. Why dot product? Why am I obsessed about the dot product as a hashing method? To start with, because it has a modulo M at the end. Why am I obsessed about the modulo M?
Because other hash function I got on Piazza private post.
Other hash suggestion of hash function that can just produce a huge number. If you are running it over 50 characters, you'll get an enormous value, and then you are trying to use this enormous value as a cell, as an index in your memory, index of a cell of your memory. And if this enormous key is much more than what you can possibly store in the memory of your computer, then this method has something wrong about it. Right? You want index that is reasonably fit into your memory. Computer, your memory, you just have like these many gigas. Secondly, these many teras on your secondary. If you have an index
that has 30 decimal digits, something is wrong.
So that's one reason to talk about why we like dot product versus, for example, just sum up the ASCII values of all the characters. Another one is that we want to is that HE and EH two words will be stored, hopefully differently. Of course, the other question that ask is it possible to have a hash function that is always good? And the answer is, of course, no, depending on the input. But at least permutation, I hope that they are going to different places. If I just sum up ASCII values, then these two words will be the same. And in general, I'll have mostly
the number of is plus a bit noise in the keys.
Okay. And the third method is, of course, all the nice properties that we already mentioned, but I'll mention again in a second. All the dot product gives us a universal family of hash functions, which makes us very happy. So dot product is preferable. I will not be very upset if you said other things, as long as it makes sense. But yeah. Oh, and there is another reason to do the dot product. Well, not where the keys are just 50 characters like in question 14, but dot product, if I have a very long file and I need to compute what is the hash value of this file, it's really convenient if this file is very long that I have to read a piece of it to my main memory, do something with this piece of it, and then I don't need this first piece once again. I can move on or read the next piece, and the next piece, and the next piece. Makes sense? And that is that I need to read every item only once. It's linear scan of the file.
And dot product does it, some other hash function also does it.
But if you're taking the whole file or key and multiply by one big number, then you see that you need this bit here and this bit over there many times. You need to read this file many times. Okay, the question with the tic-tac-toe. You can take this configuration or rotate it 4 times. So you first use, say, the dot product to give it some value. Not necessarily dot product, but we like dot product, so why not? You have to compute the dot product of this one. Nevertheless, say, express this one as 0, this one as 1, this one as 2, 0 again if it's empty, 1, 2, 1, 0, and so on. So you have some vector of numbers, you want to compute its dot product if you wish, and that's one value. And now the trick was I asked, what happened if I'm rotating it? Or another symmetric configuration in the game. You want to store all the games because you want to have some programs that will look at the game and suggest what is the best strategy for your next move, for example. So I want to take this configuration and store it somehow. But if I'll have a symmetric, one of the equivalent configuration, which would be in this case, I believe, x, rotate it, and there was an original O before I started including it, and the O will be over here, that this and this configuration are the same. So I have altogether 8 configuration, that is 4 rotation by 90 degrees plus 2 flips. 8 configuration, but you're allowed to perform only one search in the hash table. So how do you decide which of them to store? Move to the canonical form. Which would mean you gave me the first configuration. You gave me one configuration, and I'm wondering, should I store this one, or should I store this one, or one of the other configurations that I can get by rotation and flipping? I'll create the whole 8 configuration. For each one, out of this 8, I'll have to pick one, and that will be the one that I stored. How? what is the rule about the canonical configuration? That if you see it in the canonical configuration, you can say, yes, that's the single configuration that I want to store. So it's not the only solution I would think about. Look at the dot product of all the 8 configurations, compute all of them, and see which one gives you the minimum. And that's the one that you store. Pick the one that is the maximum, pick the one that you like the most, whatever. As long as you always think about the whole 8, and you know which one you will either store or retrieve. And of course, now I'll give you another configuration as a query, and you'll take the query, rotate, and flip. You have 8 candidates. Pick not the original query necessarily, but the one that obtained by rotation and flipping, and give the minimum value. And that's the one that you are performing the search with. Again, it's completely analogous to what you did with, everybody feels convenient with moving the letters in question 14 from capital and small and capital letters always into small letters. That's the same thing, exactly the same thing that I'm doing here, except that now it's rotation instead of moving a letter from small to large, so to capital. Okay, let's get back to
I have a question. Okay, just a little bit nitpicking, but for example, if we show the minimum value as a canonical form, but what happens if we had to break even? If we had to break even between 2 of the minimum, for example, then when we search, we may search another value.
Right, so you can say here are 2 vectors. You can either look at the dot product, or you can say in either case it is a vector of zeros and ones and twos. Right? So do the lexicographical search. Now it is unique. Actually, what I'll do is look at the vectors and pick among the 8 vectors the one that is lexicographically the smallest. That would be my solution, but exactly to break ties if you have. It's one of possible ways to get out of it. But yeah, you're absolutely right. And of course, if you have tools, chess, etc., then you need this other hash function. And this question is very, very practical. If you want to do search of configurations, or for example, you have multi-agents, multi-robots, multi-UAV path planning problems, and you have a lot of configuration, and you want to optimize something about the graph, the path that multi-agents can move. Now your configuration of how the agents looks like and how you store them and how you run the extra are huge because your graph is enormous. And to start with, for low-level AI over it, you have to find a way to take configuration and hash them and store them somehow without in a way that can tell you, oh, this is already a vertex in the graph, but I'm not keeping this graph explicitly because every node of the graph is a configuration of multiple players. So, okay. More about the dot product method and formally define what is universal function. We did it in the end of last meeting, but we can say it again. So dot product, when I just have 2 keys, xi and yi, I'll pick alpha I at random, beta, I'll pick alpha and beta at random. And alpha and beta are numbers between 0 and m. M is a prime. M is a prime, which is larger than 2n. And what we proved last meeting is that if I already picked beta, yi and yj are part of the input. I don't have a control over them. I just assume that yi and yj are not the same. Because the 2 points or the 2 keys are not the same, then they are different either in the yi or in the xi, but in at least one component they are different. Let's assume that it's a yi, so I have beta times a constant. Beta I already decided, any way you want. Xi minus xj I also don't have any control. This is fixed. How many different values of alpha can I pick? Exactly m, because we said alpha is always a number between 0 and n minus 1. What's the chance that I pick the unique? Why is this unique? We discussed this last meeting, because m is prime, and we are trying to solve the question of alpha times some x0 equals y. This is fixed, this is fixed. Can we find an alpha that will satisfy this equation? Yes, but there is exactly one of them. So my chance when I pick alpha at random that I hit the one and only that caused the 2 points to collide, my chance of doing it is exactly 1 over m. Only one value of m will be bad for me. Okay, and we are playing more with these numbers. If now k is a set of points or a set of keys, and there are already n keys in it. And remember the notations that we are using all over the hashing. U is a set of all the possible keys that I might feed into my hashed function. K is a set of n students or n IDs, which I don't know yet. But n is much smaller than all the universe U. Okay, now I'm asking for if I'm picking alpha at random. So first, let's think what does picking alpha and beta at random. Now I created a family or a set of a lot of hash functions, and all the possible values of alpha and beta. Once I decided what is alpha, what is beta, I decided what is my hash function. Once I decide about one function out of the family of hash function, then I can ask, what is the probability that P1 collides with P2, that the hash function sends them into the same place, and the number is 1 over n. What happens if instead of one key P2, I have n minus 1 other keys, P2, P3, P4? What is the probability that P1 collides with any of them less or equal than the sum of collision between P1 and P2? Probability 1 over m, collision with P2, P1 and P3, 1 over m, collision with. That's a probability that P1 collides with any other key. And the answer is that it's n over m. And if you are making sure that the load factor is less than 1, load factor, or other constant that we are playing with, alpha, which is n over m, load factor. Then as long as alpha is smaller or equal than half, that is, at least half of the keys are empty, then the probability that P1 collides with anybody is less than half. Good chance that P1 is staying by itself. Okay, and here you see what are we doing if, Okay, and as you see, if we are picking keys, and if my keys are larger, not between 0 and n, but between 0 and n squared, then I just think about the key and break it into 2 parts. But here is a part that is might be unused. If this is k, and I want to decide how to break it into k0, or what we call beforehand p1, how to break it. So the first few sequence of bits, and I need to decide how long is the sequence of bits should be, and that will be k0. Next sequence of bits is k1. What would be that was xi. That would be yi if I'm not running out of bits. maybe I have Z, I over there, and so on. How do I decide how many bits can I take? The number of bits here, number of bits will be small or equal than log to the base 2 of n. Why do I want less than log to the base 2 of n? Because I want the number that I express to be between 0 and n. That's the whole thing. You can also make it variable. Just look at this number that is written here and say, I'll stop the moment that this number starts to be larger than n. But of course, it's more convenient to say, let's take just as many bits so we guarantee that we are not exceeding n for any configuration. And it's even more convenient if we decide that it's multiplicative of 8, 16, 32, and so on, because it's easier to access it. But in terms of the math, we don't care. Okay, we covered this part. If we need to pick, if my keys are between 0 and n cubed, then instead of picking only an alpha and beta at random, I pick alpha, beta, and gamma at random between 1 and n minus 1, and my hash function would be take ki and break it into the characters. Now, remind everybody, breaking into characters is nothing but think about the word ABC as the first character, the second character, the third character. Everybody feel convenient with this part, but think about the number 1, 2, 3, 4 as you can break it into a character which is 1 as one character, 2, 3, and 4. Or you can think about it as one character which would be 12, and one character which will be 34. And then this is just take this one times 100 plus this one in whichever base you want. Okay. Universal family of hash functions. We mentioned it already, but let's give the definition. By playing with alpha and beta, or with the AIs, if my keys are larger, I implicitly created a whole set of different hash functions. It's a family of hash functions. And I'm not sure why it's called a family rather than collection or a set, but that's what historically how we call a collection of different hash functions, H1, H2, all the way up to HL. Some finite number of hash functions. Again, I don't have a file with all these hash functions. To pick a member of the family, I just need to pick the constants in the dot product. The dot product, to remind everybody, was H when A is a vector and when K is a vector, you have it in one of the slides, was A vector dot product K vector, all of it mod M. So every vector A of constants defines a different member. And I want to tell you what will make our family a good family. Now, if I pick two keys, Ki and Kj, I'll always find hash functions that cause them to collide. But we made this experiment last time. Here is my hash table. 0, 1, dot, 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 n minus 1. Here is my hash table. X sits somewhere. My hash function mapped n into cell 2. Now I'm dropping y at random. What's the chance of a collision? If I drop y at random, that's it will be 1 over n. Y is completely at random because it has the same chance to be in each one of the sets. And that's as nice as it can be. That's the best I can hope from a hash function to do without looking at the data. Not to create more collisions than a random allocation will create. And at the same time, of course, it needs to be a function that will allow me to reconstruct the number. Now, if I ask you at which cell X is, I can put it into the formula and it will eventually speak the cell that I'm going to look for. Okay, so a universal family should give us exactly this property. Take every two keys, ki and kj. There are students that are not at the university yet. There are possible keys at the universe that are maybe the students that are going to appear. The probability that of a collision between them should be smaller or equal than 1 over m. And you'll find different books that define the universal family slightly different. The textbook, CLRS, will say that it should be exactly equal to. Doesn't make sense to me, so I'll go with other books that says the probability to be universal is smaller or equal than 1 over n. If it's less, even better, even fewer collisions. Meaning that if I think about all the hash function, every hash function in the family is a dot in this rectangle, it's not the hash table. It's just visualization where every point is a hash table. And I have two keys, ki and kj, in mind. Some hash functions are bad for this pair of keys. Some hash functions are good for this pair of keys. The number of bad hash functions that cause the collision is 1 over m over the all the good functions. Take a different two other keys, and you get other good and bad functions, but for the other keys, the ratio should be the same. Okay, and if you have such a family, then you're happy. Then, and dot product will satisfy it. So let's see what is a big theorem. We kind of covered it, but theorem, if I pick age from a universal family, I pick one hash function at random. What does it mean practically? I pick the constant alpha and beta, or if my keys are larger, if I'm going to generate more keys, then I'll pick A1, A2, A3, dot, AM, capital M, as many constant as I want, call these guys the vector A. Vector is just a collection of these values. That's what I mean by picking a function. And now I think about n arbitrary keys, and I'm mapping them into the n slots of the table. Then if I pick about one key x, then the expected number of collisions, the expected number of numbers of other guys that collide with x is less than n over n. We saw it already when we had only alpha and beta. But it's true in general. Okay. X, in most cases, will find itself in a cell alone. Okay, and I want to prove this theorem twice. Once without using random variable, once I will use random variable. I think that there is a reason to cover most. So let's pick any two keys, x, y. I pick one of the hash function in the family. And I'll call it a flag if I don't want to call it random variable. I'll call it a flag. There is nothing random here. I just picked in some way. Not necessarily at random, not necessarily. I just want to define what is this flag binary. Values that will be for these two keys, x and y, and for this hash function, hi. Maybe this hash function hi caused the collision, send x and y to the same cell. Maybe not. If yes, then cxyhi is 1 if there is a collision, and otherwise the 0 vanished somehow, otherwise it's 0. So let's think about the experiment. Here I have capital K consists of the keys S, my favorite key, my very privileged key S, and keep looking at it. And then I have y1, another key, y2, all the way up to yn minus 1. This is the set of students that are going to appear into the university. Here is age 1 that I'm trying to apply for all the students. Age 2, trying to apply for all the students. Age 3, all the way up to age L. L is the size of the family. And for each one, I try to apply age 1 on each one of the keys and ask, hey, X, do you collide with any of the other keys or not? And when I picked X1, then it turns out that age of X1 is also age of Y3 and also age of Y7. That is, that in this case, C of X, Y3 of, sorry, that was H1, for these cases of H1 equals 1, and this is also C of X, Y7. All the same hash function. So in this case, H1 caused X to collide with two other keys. When I use H2, maybe it collides with X will collide with a few other keys. When I use H3, maybe there are no collisions at all. I want to ask how many collisions the average hash function will be. I'm going to sum up the number of collisions. I'm going to sum up the number of all the collisions that are happened for all the values of all the keys, and for all the hash function, and for all the values. And then I'm going to divide it by the number of members that I have in my family, because that's what the average hash function is doing, picking a value from the general value number. So once again, I pick one of these functions, hi, keep it fixed for a moment, look at all the other keys y in k, you can limit yourself to only keys that are not x, and ask for this hash function hi, either a collision, and I'm summing it up for all the values, all the keys over here. And since I want the average behavior of the hash function for the family, I sum it up for all the members of the family. And of course, I take the average divided by how many members do I have in the family. Some are good for X, some are bad for X. I want to know what average number. So look at this double summation, and what do I do when I see a double summation? I switch the indices. It's uncontrollable reflex. It's 1 over age. Now I sum up in the outer summation became 1, so I sum up stuff for the y. And now I pick y fixed, and for x and y, just one pair, I sum up for all the hash function and ask, hey, what is c, x, y, of age I for this one particular number? Which asks what? Now x is fixed, y is fixed. And you're summing up either a collision, yes collision, no collision, yes collision, no collision, for this pair x, y. And look at this sum that happens here. What do we know about universal families? That no matter what is x and y, as long as they are different, of course, the number of members of the families that caused x and y to collide will be the size of the family divided by n. That is a probability that when you pick a hash function from the family that you picked a bad one will be 1 over n. And the number of hash functions that are bad for x and y is not more than 1 over n percentage of all the functions. Number of functions in the family divided by n. that's how many times you're getting 1 here as a cxy of age 1. Okay, so if the family is universal, then this number in the inner sum is less or equal than how many functions do you have divided by m how many cells. And we are actually done. Because what do I do? I sum here for all the y's in k, no more than n other students. It's realistic input. No more than n minus 1 to be precise, realistic input. And I sum up what? This constant term. How many times did I sum it up? N, actually n minus 1, many times. For every y in k, which is not x, so it's 1 over h that I'm dragging over here because I average by the number of hash functions times this sum is nothing but n times this constant, h here, carry each other, n over n. Exactly what the theorem wanted to do. Okay. If you want a proof with random variable, now c over xi is a random variable, it's 0 or 1, depending on whether the hash functions that I pick at random creates a collision or not. I'll also define capital C of x, that is how many keys are colliding with x, that is, how many keys are colliding with x. What is the probability of C xy? It's a Boolean variable. Writings here. C over xi is just the probability that cxi is 1. We have this exercise many times. So this is just 1 over m. What is capital C of x itself? It just sum up this Boolean random variable, how many collision x has with any other member of the family. What is the average value? Average what? Average on when I'm trying all the functions. But it is E of xy, it is the expected value of the sum of the cxy, which is the sum of the expected value of the cxy, which is, once again, n over n.
Okay. Two ways to say the same thing.
Metal preferred. Okay. Here are the slides from the original lysosomes set of slides, which just repeat what we said about when I simplified it in the previous slides for only alpha and beta. Here you see how you break a key for possibly R plus 1 many pieces, and asking how many functions do I have. The number of functions is all the values that I can generate, how many different can I generate for the vector A. All I need to take is the first constant, the second one all the way up to the R constant. So it's m to the power of R plus 1. What's the probability for x and y that they are colliding? You see the slide here? Yeah, what a probability. There is a slide that I skipped, but it's in the set of slides. That essentially just says that it is universal family, and you're just getting the same reasoning that we had earlier. How many bad families you have? Well, if you have 2 keys and you want 2 keys to be equivalent, you can pick A1, you can pick A2, you can pick A3, all the way up to AR, and you still have one constant A0 that you can pick. And to create a collision, there is only one value of A0 that will be bad for you. Just equivalent to one value, one bad value of alpha. Okay. I'll rejuvenate the slides, but it's essentially said exactly what we had before. So that's the total number of functions, and the number of functions that create a collision, bad functions. I only have choices for R values, but once I picked R values, then the R plus 1 values is uniquely determined, so the bad functions you have m to the power of R. What's the probability of picking one bad function? It is m to the R divided by
m to the r plus 1, which is 1 over n.
And I want to talk to you about perfect hashing. So a lot of the power of hashing is coming when we are,
our data is dynamic, is changing. We don't know what are the keys, and they are just going to appear once over time.
But what happens if I don't need it in a dynamic setting? Actually, happy with the static setting. You will give me the set of keys, and keys I'll decide about n, which is usually twice. I'll decide about n and prepare a hash function, but my condition is that the search will take order 1. In the workspace. I don't want average, I don't want anything. I want that there will be no collisions at all. So how can I use the universal families and to create a hash function with no collisions at all? So here is my first attempt. I will pick. I'll try to think of a deterministic algorithm. It turns out to be much more complicated. So instead, I'll go for randomized approach. I will pick a universal family of hash functions. But if I'm keeping m and n to be roughly of the same size, there is no hope. Universal family will cause few collisions. But one of these n annoying keys, one has to collide with somebody else. I cannot avoid it, even if I pick universal family, as long as n and m are of the same size of magnitude. What will happen instead if I pick m to be quadratic, m to be n squared? Huge memory, and again, it's only my first attempt, but it's important attempt because I will kind of use it, but not in the way that I described it right here. So what happens if I pick m to be n squared? Much more memory than I need. I have 10 gigabytes of keys. I pick 10 gigabytes squared as the size of my hash table. What will be the number of collisions right now? Number of collisions now will be the same C of x, y, h that we just saw, which will now be how many pairs of x and y do I have to do? The sigma here, notice it's not the sigma only of the y, the sigma of all the pairs of x and y. I look at any two keys in the set of keys. Remember, you know what is the set of keys. There is no surprises here. I'm building the function for a given set of keys. I'm running over all the keys, x and y, and compute do they collide or not collide? Collide or not collide? So it's n times n choose 2, that's the number of pairs of keys they have, which here, and the chance of the collision is 1 over n. So when that settles, we have n, and what is n choose 2? It's n minus 1 half. This half is somehow important. The probability of collision is 1 over n. So we have half times n squared divided by n squared less than half. So now that's the probability of any collision, any key collide with any other key for a huge hash table. Now, how can what does it mean algorithmically? It means that if I pick my hash function at random and use Markov inequalities that I'll mention a bit more next meeting, Markov inequality will tell me that the probability that you're getting more than half the number, more than half, if it's more than one collision, that you're getting one collision or more, this probability that there is any collision is less than half. The probability of any collision is less than half.
Okay, so what's the algorithm? Again, for the moment I'm happy with the n squared memory.
How do I make it into an algorithm? It's a randomized algorithm, but it's different than the randomized algorithm that we saw already. It's similar from my question about how do you pick 3 students with equal probability with coins. Well, the solution was there is a chance that our experiment will keep on going forever and ever, just a very small probability. Remember, it was head, head, tail, 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 and tail, head was, let's do the experiment once again. So, once again, what I'm doing right here, I'll pick a random function from the universal family. If it works for me, great, I'm done with this part of the algorithm. If it doesn't work, dump it, take another function at random. If it works for you, no collision, easy to check, great. There is collision, dump it, do it again. What will be the expected running time? Expected running time depends on, with probability half, I need one experiment. With probability of 1 over 4, I need 2 experiments. Probability of 1 over 8, I need 3 experiments. Right? It means that it didn't work in the first experiment, didn't work for the second one, didn't work for the third one. I need at least 3 experiments, probability of 1 over 3. So it's a sum of I divided times 1 over 2 to the I. It's not geometric sum, but it's actually going up, even slower than the geometric sum, and we will use the result. That's the expectation of such experiment. The number of trials that you need on average is 2. So it just reinforces that this algorithm that is randomized, after 2 experiments, you're very likely to pick a hash function that is good for you, because the probability of picking a hash function that is good for you is at least half. Okay, so let's just flash one slide. How do I actually now get to one reasonable hash function? I don't want to spend n squared time. I don't want to spend n squared memory. It's way too much. So what do I do? I'll pick one hash function from a universal family, and I'll use a table of linear size to it. And now, what do I know? Every key only collides with a few other keys, not too many other keys. Maybe it collides with 2 other keys like here, maybe it collides with nobody like here, maybe it collides with only one like here. That's we can guarantee with high probability. That is that if I think about the set of who collides with whom, S1s are everybody that is mapped into slot 1. S4 is everybody that is mapped into slot 4. These sets are small. So what's the trick? For such a small set, I can allow quadratic space. I can allow the quadratic space that we saw in the previous slide just for the set S6. I can allow quadratic space, but only for the set S1. It's quadratic, but it's quadratic in very small quantities. So when I sum up how much memory do I need here and here and here, it's just the sum of the square, which we already see. It is linear. So altogether, I'll need, with high probability, linear space altogether. How does my hash function work? You will give me a key. I'll go to my first hash function that just tells me, go to this other hash function and ask this one, and now you'll need another lookup in a much smaller table. So altogether, you have n plus 1 many tables, but the search takes lookup in the first table, lookup in the second table. The memory will be linear, and there are no collisions at all. Okay, that's clever. And it's described very nicely in the book. You can get ready for Wednesday. The cuckoo hashing are not in the book. That will be newer material, became popular hash function recently. And maybe we'll talk a bit about Bloom filters that are very, very important when we look for intersection of documents, looking for words in documents, communications, another application of hashing that are not just storing parting data, not just retrieval of data. Thanks, everybody. Questions, please, anything?